Hello, and welcome back to the course on University Physics 3. We are now on Chapter 10 of the course, which will talk about inductance. So we'll focus on two inductances, the mutual inductance and the self-inductance. So before we proceed, let us first review some of the concepts that we have learned in the previous lessons. So we have learned about Faraday's law, which is the induced EMF due to a changing magnetic flux. So our first lesson will be on mutual and self-inductance. So when the current in a coil changes, the flux in a coil changes, it will induce an EMF in another coil. But it will also induce a coil on itself. So there will be mutual induction and self-induction. So mutual inductance describes the coupling between coils. So the induction between coils. So coil 1 induces a coil on another coil and vice versa. So suppose you have this is coil 1, this is coil 2. So if the current in the coil 1 is changing, meaning the flux is changing, the magnetic field is changing, it will induce a current, an EMF in coil number 2. And since the induced current and induced EMF is also changing, then it will induce another EMF back to coil number 1. So the mutually induced EMFs are given by these values here. So it's proportional to the change in current, di dt. So this is the induced EMF on coil number 2 due to the change in current in coil number 1. And this is the induced EMF in coil number 1 due to the change in current in coil number 2. And M is just the factor called the mutual inductance. So it's related to the number of coils and the flux through loop 2 due to the field of loop 1 over I1. Or it can also be equal to the number of turns in coil number 1, the flux in loop number 1 due to the magnetic field of loop number 2 over I2. So the standard unit, the SI unit of mutual inductance is Henry, and 1 Henry is 1 Weber per ampere, or 1 volt second per ampere, or 1 ohm second. So an example is if you have a rechargeable toothbrush or a rechargeable device which uses wireless charging. So I guess the wireless charging technology for smartphone is now available, and that takes advantage of the phenomenon called mutual inductance. So there is a coil in the base of the toothbrush. There's also a coil in the base of the charger, and the way to charge the toothbrush is to change the current in the coil, in the base coil. So it will induce a current in the toothbrush, and that will charge the battery in the toothbrush. So that's wireless charging, essentially. So let's have an example. So a solenoid with length 0.50 meters and a cross-sectional area of 10 centimeters squared, so this is the yellow solenoid, is closely wound with 1,000 turns of wire. Another coil, a gray coil, with 10 turns, surround the yellow solenoid with their axis at its center. So you're asked to find the mutual inductance, and the current in the gray coil is given by this one. The current gray coil is coil number 2. The yellow coil is coil number 1. So I2 is 2 times 10 to the 6 ampere per second T. So what is the magnitude of the induced EMF in the solenoid or the yellow coil? Okay, first problem, find the mutual inductance. So there are actually two formulas. You can just choose either of them. So we have for letter A, I'm just going to use this one. So number of coils for loop number 2, and then the flux through loop number 2 over I1. Okay, so the flux through loop number 2 is just due to the magnetic field of loop number 1 times the area. So we will assume that they will have the same area. They are closely wound. So they approximately have the same area. A1 and A2 will have the same, approximately the same area. Okay, so the magnetic field of a solenoid B1 is actually given by mu naught N1 over L times I1. So this, we have obtained this before when we try to find the magnetic field of a solenoid. So Ni over L is just the number of turns per unit length. So this is N1. So we substitute this to this, and we substitute this to that, and we will get N2 times mu naught N1 over L I1 times A over I1. So I1 will actually cancel out. And you are left with mu naught A N1 N2 over L. So all of these values are already given. The area is given, number of turns for loop 1 and loop 2 are given, the length is given, and substituting all the values, you will get 25 microhenry. Micro means times 10 to the negative 6. So 2.5 times 10 to the negative 5, or 25 times 10 to the negative 6 henries. That is for letter A. So that is the mutual inductance. So letter B, if the current, the gray coil, is given by that, what is the magnitude of the induced EMF in the solenoid? So for letter B, the magnitude of the induced EMF in coil 1 is equal to negative M change in current in loop coil 2 dt. Okay, so I2 is given. So the derivative of this with respect to T is basically just that one, 2 times 10 to the 6 ampere per second. So we have our mutual inductance is 25 microhenry. So micro means times 10 to the negative 6. And derivative of our current with respect to T is just 2 times 10 to the 6 ampere per second. So the final unit of that is volts. And you will get a value of negative 50 volts. Again, the negative sign implies that the induced current in coil 1 is opposite the direction of the current in coil number 2. So that they are opposite, the currents are in opposite directions. So if the current in loop number 2, if this current is counterclockwise, then the induced current in coil number 1 or in the solenoid is clockwise. So that one. So here are the summary of our results. So the magnitude of the induced EMF is 50 volts. Okay, so let's now go to self-inductance. So I have mentioned before, if the current in a loop is changing, then that will also induce an EMF on itself. So it's called self-inductance, or basically just inductance. When you say inductance, we mean self-inductance. So if the current in the coil is changing, the changing flux of the coil induces EMF on itself, on the coil itself. So the self-inductance or the inductance is given by the symbol L, and it's just the number of turns, the flux, and over the current. And the self-induced EMF is just negative L di dt. So it has the same format as the mutual inductance. So an inductor now is the third basic element of a circuit, aside from a capacitor and a resistor. So you have an inductor. So it's a coil with specific inductance. Sometimes it's called a choke. So examples are the magnetic ballast in your fluorescent lamps. and spark plug. A spark plug is an inductor. So the symbol for an inductor, circuit symbol for an inductor is basically coil. So it looks like a spring. So magnetic ballast, the fluorescent light tubes are wired in series with an inductor, or what we commonly call a ballast, and that the ballast actually helps sustain the flow of current through the fluorescent tubes. So if the current suddenly decreases, then the inductor will induce a current, and vice versa. If the current is increasing, then the purpose of the inductor or the ballast is actually to regulate the flow of current. So it doesn't want any changes or variation in current. So similarly, there are inductors in your electrical power transmission systems, in your electric poles. So if you see these things here, the brown ones that looks like spirals, those are inductors. That is to protect the electrical transmission system in case there is a rapid change in current, such as if it is hit by lightning. So the inductor will actually absorb all of that energy if it is hit by lightning, and it will just release that energy later when the current is decreasing. So when the current suddenly increases, such as being hit by lightning, the inductor will absorb that energy, and when the current is decreasing, the inductor will release that energy. So here's the difference between a resistor and an inductor. So if current flows through a resistor, there will be a potential drop in the resistor, and it's equal to the current times the resistance of your resistor. But if there is a constant current flowing through your inductor, there's no voltage or potential drop in your inductor because there's no change in current. But if the current is increasing, then there will be a voltage drop in your inductor, and that will induce an EMF and current in the opposite direction to oppose the increasing current. That is always how nature reacts to any changes in flux and current. So in another case, if the current is decreasing in that direction, then there will be an induced EMF in the same direction to support the decreasing current, so that the current will, as much as possible, remain safe. So as I mentioned before, in the example on getting hit by lightning, electrical pole getting hit by lightning, that it stores energy. So an inductor actually stores magnetic field energy, and that energy is actually stored within the magnetic field in the same manner as the energy is stored in the electric field inside a capacitor. So this is the maximum energy stored in an inductor when the current reaches a final value of I. So it's 1/2 Li squared. So as comparison again with the resistor, so when current flows through a resistor, energy is dissipated, meaning energy is lost. But when a current flows through an inductor, energy is actually stored or released. So energy is stored when the current is actually increasing, and energy is released when the current is decreasing. So that is the purpose of our inductors. So it stores current when the current is increasing. So if there's a surge in current, the inductor will store current. But when there's a deficit in current, then the inductor will release some current. So the energy required to fire a spark plug in your motorcycles or cars is derived from the magnetic energy stored in the ignition coil. So a spark plug is another type of inductor. So let's have an example. So you have a toroidal solenoid. Actually, we have presented this before in our previous lessons, with a cross-section area of 5 centimeters squared. So that is the cross-sectional area of the section of the toroid. So the section of the toroid is actually a square, and its cross-sectional area is 5 centimeters squared. And its radius is 0.10 meters, and it has 200 turns of wire. And the toroid is wound in a non-magnetic core. So this yellow thing here is non-magnetic. Okay. So determine its inductance, assuming the magnetic field is uniform, and if the current in the toroidal solenoid increases from 0 to 6 ampere in 3 microseconds, find the magnitude of self-induced EMF. Okay, first question. So determine the inductance. Okay, so to solve for the inductance, we need to know the number of turns and the flux and the current. So the flux in this case is just B times A, and the magnetic field of the toroidal solenoid is actually mu naught, the number of turns, times the current over 2 pi times the radius. So we have just check this one again. So you can actually obtain this using amperes. Okay. So we substitute this to this, we substitute this to that, and you will get N times mu naught Ni over 2 pi r times A over I. So the I will actually cancel. There's an I here, there's an I here, we don't need the I. And we are left with mu naught N squared A over 2 pi r. So all of these values are given. The cross-sectional area is given. Just convert that into standard units. The radius is given. It's already in meters. So that's good. And that's it. Mu naught is just a constant. 4 pi times 10 to the negative 7 Tesla meter per ampere. And you will get a value of 4 times 10 to the negative 5 or 40 microhenries. So the self-inductance of this toroidal solenoid is 40 microhenries. Okay, so that's the inductance. Okay, if the current in the toroidal solenoid increases from 0 to 6 amperes in 3 microseconds, find the magnitude of the self-induced EMF. The magnitude of the self-induced EMF for an inductor, so we'll just use the absolute value sign to signify that it's a magnitude, because there's a negative sign in the actual formula, is L, and the magnitude of di dt. So you have L, and the rate of change of current is this one, 0 to 6 amperes in 3 microseconds. So you have 6 amperes increase in 3 microseconds. So L is actually 40 microhenry. We have already solved it earlier. So that's 40 times 10 to the negative 6. So that's microhenry. And you have 6 amperes in 3 microseconds. Micro means times 10 to the negative 6 a second. So the final unit of this is volts. You will get a value of 80 volts. So this is the magnitude of the induced EMF in the toroidal solenoid, the self-induced EMF. So it's 80 volts. So these are the summary of our results. So for our last example, this is an example of magnetic field energy. So the electric power industry would like to find efficient ways to store surplus energy generated during low demand hours to help meet customer requirements during high demand hours. So actually this is what happens in our electrical power system. During low demand hours, during the night, for example, inductors actually store energy. And during high demand hours, they release that energy to the customers. So perhaps a large inductor can be used. So what inductance would be needed to store 1 kilowatt hour of energy in a coil carrying a current of 200 amperes. So the 200 ampere current is already the maximum current flowing in your wires. So magnetic energy is just 1/2 Li squared. But we are trying to solve for L. So therefore, L is equal to 2U over I squared. So before we can solve this, I is 200 amperes, but U is still in the layman's unit of energy, which is kilowatt hour. We need to convert this into standard units, which is joules. So U, which is 1 kilowatt hour, convert this. So 1 kilowatt is 1000 watts, and then 1 hour is 3600 seconds. So the unit watt second is the unit called joules. So kilowatt, kilowatt, hour, hour, and you have watt second or joules. And this will give you a value of 3.6 times 10 to the 6 joules. 3.6 times 10 to the 6 joules. So therefore, L is just equal to 2 times 3.6 times 10 to the 6 joules over current, which is 200 amperes squared. And the final unit of that is Henry. And you will get a value of 180 Henry. So similar to capacitance, when the value of capacitor is already in farads, that's actually a very large capacitor. So usually commercially available capacitors are in the microfarads or nanofarads. So similarly for inductors, it's the same. Usually commercially available inductors are in microhenries or millihenries, and the ones that are used in systems like power transmission systems are actually in the level of henries, 180 henries, 180 henries in this case. Okay. So that is the end of this lesson, the first lesson for this chapter, the chapter on induction. For the next lesson, we will try to analyze what happens in an inductor when you couple it with a resistor and a capacitor. So inductors in circuits. So I will see you again in the next lesson.